My name is Perry Alexander. I'm from the University of Kansas, and today I'm going to present some work that I've done with my colleagues, with my students predominantly. They're listed here. You can't have them yet. They're not done, but when they are, have right at it. I also have been working a lot with MITRE, Josh Gutman and Paul Rowe, predominantly, and the government is a wonderful thing. I just got permission to add Jim Carter and Steve Smalley, who I've been working with, to my slides as I was sitting back here, and I'm afraid to modify slides this close to a presentation. So I have to give due credit to Steve and Jim. So I'm going to talk today a little bit about some work we've done recently on remote attestation. This talk it's about attesting to a cross-domain system, but it's really not about that. It's really about building a general purpose semantic remote attestation system. So I've been working with semantic remote attestation for years, starting with TPM 2.1 and building secure virtual machine systems with NSA years ago, and working through that to now. And what I'm going to share with you today is effectively a story. I'm not going to argue that we have a perfect solution yet, or ever, but certainly not now. But we've been working in remote attestation, which I've described here, but we've been working in this space for years, and we decided that it was time to put everything together. It was time to build a system all the way from boot through runtime measurement and remeasurement. As I said, we built the parts before, we talked about this, we did a lot of modeling and verification, we just decided it was time to do the whole thing. So what I'm going to talk to you about today is that story, in effect, how we did this. So when we talk about remote attestation, I think we kind of have the classical definition. We have a relying party that wants to trust or establish trust in a target system, sends that target a request. The target gathers information and packages it up, signs it typically, sends that information to an appraiser that then makes a report back to the relying party. I think this is a very standard definition. We follow it fairly carefully. And as I said, what we wanted to do was take our implementation of this and apply it to a system. And as we talked with our sponsors and our friends, one of the things that came up was this notion of a cross-domain system. Now, the system that we're looking at isn't it's not a truly fielded cross-domain system. If you work in that area, I'm not going to pretend that this is a serious cross-domain system, but it has some of the properties that we wanted to have, and it's a system that we didn't write. And that was important to us. We wanted a system that wasn't ours, that we could implement an attestation system around. So our research goals were then to establish TPM as a functioning root of trust. We wanted to start at boot. We wanted to start at the beginning. We wanted to bring up a trustworthy runtime attestation system. And we wanted to perform runtime attestation on this cross-domain system. And we wanted to start doing some empirical testing. One of the things we realized we had never done was to sit down and actually run these things at length and try to establish what's good and what's bad, to do some empirical testing. The tools that we're going to use, I think it's first of all, I'll talk about our architecture for remote attestation in just a second. But we use the Copland attestation protocol language, which is something that we developed in conjunction with APL, MITRE, NSA, also our sponsors at Honeywell. But we developed a language for representing attestation processes. We have implemented this as a part of an attestation framework we call Maestro. Maestro is formally verified. I have to confess, my background is first and foremost informal methods, and I come to this stuff later. But one of the things we wanted to do was establish that our Maestro toolkit was formally verified. This includes a general purpose attestation manager that runs our protocols, and I'll talk about that to some degree later. And finally, we're using Envery's LKIM tool I don't know if folks are familiar with LKIM or Invery. I have to kind of come clean here and say that I'm a co-founder of Invery, so we kind of had special access to LKIM. But if you're not familiar with LKIM, I'm not going to explain how it works. It's a general purpose Linux integrity kernel measurement tool that was developed by APL for NSA, and they've licensed it to us, and we've been taking on commercialization of it. So this is kind of the architecture. This is the architecture of the system that we want to implement, and it follows an approach that Coker, Lascoco et al. Called out in Principles of Remote Attestation several years ago. That's kind of our guide for what we were trying to implement. So if you're familiar with Mott, the way we build an attestation manager is somewhat familiar with the way that Mott builds theirs. But what we've got is a layered system, and layering is very important to us. At the top, we have a target, and in this picture, I hold the target generic because I'm going to argue that once we get this thing up and going, we can attest to whatever we want to. We have an M&A subsystem that sits beneath that, which consists of an attestation manager that's capable of running protocols, and a collection of attestation service providers that provide the measurement and processing capabilities for those protocols. So the goal is to get this thing up and running and hand it whatever protocol we want it to use to attest to a running system. So M&A subsystem, underneath that is the operating system, and we have to bring up, the M&A system depends on the operating system, so we can't just bring the thing up. We've got to bring it up into a trusted state so that we can basically transfer trust to the M&A system. And finally, we have our classic roots of trust at the bottom. So this is the system I'm going to talk you through building, the story of how to build this system all the way up to the beginnings of our runtime attestation. So also a part of this is evidence and our attestation manager signing key. Both of these things are very important to us. First is evidence. We have an evidence semantics that is associated with Copland. It composes evidence that's generated by our attestation service providers. It composes that in a principled way that indicates it indicates what order the evidence is gathered in. So we'll have a collection of evidence. The double semicolon in this case happens to be sequential. We have other ways of ordering evidence, but it turns out that in these systems, the order we gather evidence is essential. We've got to know that dependencies are measured prior to the things that depend on them. Therefore, we've got to make sure in our evidence that that's indicated. And then finally, this attestation manager signing key. We're going to work very hard to set up a key associated with our attestation manager that provides a strongly bound ID to that attestation manager. We want to know that when a signature is checked and checks well, that it's associated with, that the evidence is associated with exactly the attestation manager that produced it. The other thing that's very important is we want this key to be accessible to the attestation manager only when the system underneath it booted properly. So everything has to come up properly, and then the key has to be bound to the attestation manager, and then it will use to generate a signature. So here's what's going to happen. We're going to boot the thing we're going to boot our system up to the attestation manager. The attestation manager will have access to its key, we hope, if everything went well. And any signature to that key will say, hey, this attestation manager produced this evidence. And also that because the key was available, we know that the system booted in a trustworthy way. Okay, so when we check our evidence, we're going to check proper bundling, that it was put together properly, that our evidence satisfies an appraisal policy, and finally that we have a valid signature. And if we can do that, then the target that we care about, we're going to say there is at least evidence of its trust. Is it 100% trustworthy? Of course not. But we've got strong evidence that we can establish, or we can place some trust in it. So I'm going to build this thing from the bottom up. We're starting at the bottom with the TPM. It's going to be our root of trust for storage and reporting, as always. It's trusted a priori, as always. Nothing magic here. We're using a TPM 2.0. We used to do this with a 1.2. 2.0 is way better. It's way easier to use. It's going to also store our key. We're going to use this key in our attestation manager, but it's going to live in the TPM. It's going to be resident in the TPM. We also, as our other root of trust, the EFI, the firmware, that is going to be our root of trust for measurement. It'll get the bootloader going and perform the first measurement that starts our system. So there's nothing magic here about our roots of trust. They could be others. I've built this system or similar systems using a SEL 4. I've built them with other, various other one software root of trust. We really don't care about these roots of trust. We just care that they are roots of trust. TPM makes a lot of things a lot simpler, so we're quite happy to use a TPM. So the first layer that we have to build is the layer that everything else depends on. We'll call it the operating system layer. We're going to measure and start Linux. We're going to measure and start SELinux, and we're going to measure and start IMA. We use these, and these are standard things. Yes, we use them quite heavily in building out our system. So this is a picture of what this boot process looks like. It's not particularly different than the standard way of going through boot, but there are a couple things I do want to point out as we go through it. So we're going to start out, as I mentioned, the firmware is going to measure the bootloader and start it. And the bootloader is then going to load an ITRAMFS and a command for starting that system. Now, an ITRAMFS for us contains the classic stuff that it always does. I call it the boot material, the stuff that will allow us to get our system up. It also contains a script that we use to measure, to hash the two policies, the IMA policy and the SELinux policy. The reason for this is I want to seal my key, that attestation manager signing key. I want to seal that to those two policies. I do not want that key available if either my IMA or my SELinux policy is bad. Okay? Now, they do get measured anyway. They get measured into PCR10. IMA takes care of that. But PCR10 is not usable for for sealing. It changes. It's always changing, actually, but it doesn't have predictable values all the time. It's just not useful for sealing. So we're going to measure our two policies that we care about, and also the init script into PCR11. But as I said, we boot in kind of the classic way. The bootloader is measured into PCR4. We measure an ITRAMFS into PCR9, the command line that starts it into PCR8. And I mentioned that once we've done that, we bring the core operating system up. Our special policy measure script runs and populates PCR11 with measurements of our two policies. We could choose any PCR for that. It doesn't have to be 11. We also have thought about mixing it in with another or measuring it into one of the already used PCRs, but we didn't want to take a chance on messing something else up. So we chose PCR11, but you could really choose anything you want. So by the time, and then of course, we switched to rootfs, and at that point, Linux is up and booted. We, as I said, we have these measurements of our two policies in addition to measurements of our system. So a little bit of foreshadowing, what we're going to do is seal our key, seal our measurement key, our measurer's key, seal our attestation manager key. We're going to seal that to PCRs 4, 8, 9, and 11. And what that will do is make that key unavailable if the things that are measured are in a bad state. So once we get up, once we're booted and going, now we have a good PCR4, which indicated a good bootloader, a good init RAMFS. It also had good PCRs 8 and 9 indicate that our init RAMFS and command line were in good state. PCR 10 we ignore, as I said. We can't use it for sealing, but we could use it to rebuild the IMA log or IMA key or IMA hash if we wanted to. And then finally, we've got a good PCR 11, which is our stuff, which is the stuff that we measured in. So at this point, we now start our stuff. We start running what we call the runtime attestation layer of our system. So I'll walk through this, but we measure and start the attestation manager. We establish ASP libraries that it uses for its work. We ensure, this is a little bit of a misstatement, we try to start using the AM signing key, and we start executing Copland protocols to measure things things in the runtime. So AM inverse, the attestation manager signing key, is basically when I protect and use that, as I said, we seal that key to PCRs 4, 8, 9, and 11. So as it exists in the PCR, or as it exists in the TPM, the key will not unseal unless we have those PCRs in a good state. So the way that it's generated, though, is we have a key blob that resides in the attestation manager. And the attestation manager asks the TPM to reproduce that key, and also load an authorized TPM policy for that key. So what we're going to do is we will rebuild the key or construct the key in the TPM. We'll load that TPM policy. That TPM policy has to be authorized, or the TPM key will not be available. And now at that point, we have a way to send things to the TPM or have TPM sign things for us. So the key blob that we build the key from resides in the attestation manager. And it is protected itself by SELinux policy and also IMA policy. So we are certain that only that attestation manager can get at that key. So the story we're trying to build up, or the argument we're trying to make, is that when that attestation manager uses that key, it's using the right key, and only that attestation manager can use its key. And in addition, that key is protected by sealing to PCRs. So what we're going to argue now is that anything that I sign with that key is going to carry evidence that it was produced by a system that came up properly. And that's very important to us. We can't ask someone to trust the evidence that we gather at runtime if the system that gathers that evidence doesn't come up in a good way. So at this point now we have a general purpose runtime attestation system. We haven't talked about our application yet, but we now have the ability to measure pretty much whatever we wanted. And this was the goal, the work that we did early on with MITRE and NSA. This was our goal. This was effectively what we wanted to do. We wanted to get an attestation manager set up in such a way that we could add things, that we could ask for it to, we could develop new measurement capabilities, new appraisal capabilities, and build them on top of this attestation management subsystem. Also we have a standard way of representing evidence so that once that evidence is gathered, we can hand it to external appraisers to look at it. Okay, so now we have a system that's ready to go. This was our first goal, getting our measurement system up and going. Now the second goal was to start thinking about the application we wanted to attack, which was this notion of a cross-domain system. I'm pretty sure everyone is familiar with what cross-domain systems are about in this room. That's not always the case, but as a quick review, I'm going to pull messages off the high side, and I'm going to process those by an intake server. It's going to write those to a buffer. those messages, and in this case, we are actually cleansing email messages. Those messages are rewritten, and the rewritten messages go to a filter, and that filter decides which messages should go forward or not. And then finally, the messages that have been rewritten and filtered appropriately are exported to the loci. What the cross-domain system specifically does is really not important to this story. It's just simply an application that was given to us. And again, it was important to us to have a real application that someone handed us. So several things about the cross-domain system, that they are, the rewriter and the filter both have configuration files. This turns out to be fairly important when we start thinking about designing things to be attested to. And we want to assure that every message that gets from one end to the other, it started from the high side, it was rewritten appropriately, and it was filtered appropriately. We want to make sure that that's the case. At that point, so someone's handed us this application. At that point, now we want to think about building an attestation system specifically for that app. So the first thing we start thinking about is what the adversary might be after. So now we're starting to think about what the adversary might do. And in this case, there are a whole number of things that an adversary might attempt. It might go after configuration files. It might try to replace pipeline binaries. It might interrupt communication paths and buffers. It might try to exfiltrate and infiltrate messages from the pipeline. It also might try to attack our SELinux policy or try to attack our IMA policy. And one of the things that is interesting here is that I've listed these on my slides in terms of which is hardest. What I'm trying to do, ultimately what we're trying to do with attestation is not protect the system from everything. That's not what attestation is about. What I'm trying to do is make the adversary work as hard as possible to defeat the attestation system. So if I can force the adversary into trying to modify installed IMA and TPM policy, I've won in a way. I've won. If I can protect the configuration files, which are easy to modify, if that attack is not detected, if that attack gets through, then I've not won. So the idea is to use attestation to make this process as hard as possible. So now what we need to do is come up with an attestation protocol that takes care of, that monitors or measures all of these components in the right order. So the first thing that we do is we start to think about this. I've added SELinux in because one of the first things that we do is measure the SELinux policy. We use LKIM for this. It's not configured in any magic way, although we do have a little bit of privileged access to it because of the association between KU and Invery. But the first thing that we do is measure LKIM, and it's important that that occur first. The next thing we want to do is measure out the running SELinux policy. So not only do we need to know we have a good LKIM, we need to know that LKIM is running our good policy. And remember, we measured that policy earlier. We can now start to compare measurements of policies to make sure that this is the correct one. At this point, we hash our configuration files. So as I said, both of the core binaries of the cross-domain system have configuration files. We hash both of those. And then finally, we hash our binaries. This is important. The order of this is important. The SELinux policy depends on having a good SELinux. The configuration files depend on running on a good SELinux system that can protect their access. The hash binaries depend on the binaries depend on the configuration files, depend on SELinux, so on and so forth. So the fact that these happen in this particular order is critical. If they're not in order, then we can't guarantee the fidelity of the measurements. And then finally, we're going to generate a signature on all this. So What we want is an attestation protocol that will perform our 4 measurements and then generate a signature for our results bundle or our evidence bundle. So the very bottom of the slide, the thing that appeared, this is the actual attestation protocol that we use. It's written in Copland. This is standard Copland concrete syntax. It's not really meant to be read by humans, but this one in particular is fairly easy to read. It says that at our attestation manager, we're going to run these 4 attestation service providers in order and bundle the evidence, and then finally generate the signature. And that signature is generated with the key that we work so hard to generate and protect. Right? So once we're here and once we have this signed, we've worked very hard to get that done with our signature. So when this thing is running, when the attestation protocol is executing, we still have to worry about protecting it. We can't just ignore it or let it run on its own. We still have to worry about protecting it. And the way we do that is, I've talked about the AM signature, and I won't talk about that again. We've talked about Linux and using LKIM for that. We also use IMA to protect the attestation service providers to make sure at least that the right binaries are loaded. Now, we don't do anything more than that right now. The right binary might do something that we don't want it to do, and we'll come back to that as work later. We use, as I said, we use IMA to take care of our ASPs as they run. Okay, so finally, we get this stuff back. So we run our attestation protocol. I mentioned evidence packages, and this is the form of the evidence package that's generated by this attestation protocol. We're going to check our 3 properties: proper bundling, appraisal policy, and valid signature. So our proper bundling is indicated by the sequential operator telling us which piece of evidence was gathered first. I should back up for just a second and say that our attestation manager itself is formally verified. I said I'm a formal methods guy by training. The first thing that we thought we needed to do, and we thought would be sufficient and wasn't, was to verify the attestation manager. So we know that an attestation manager will execute a Copland protocol according to its semantics. So I know that if I handed this attestation protocol, whoops, I'm using my mouse. If I handed this particular attestation protocol to the attestation manager, it will produce evidence in the order that we specified in the protocol, period. So we can count on that. So we do have we check for proper bundling. Each piece of evidence has some policy that we check. In this particular case, LKIM has its own analyzer. It has its own, I believe they call it a verifier. It has its own verifier that checks the results from SELinux. The others are simply hash checks. We check those hashes, and we can now appraise whether our system is in a good state or not. This introduces some provisioning requirements, which kind of make things a little bit more difficult. I've got to gather good hashes. I've got to then distribute those good hashes to whatever appraiser might be using, or whatever appraiser might be looking at our evidence. I've also got to take care of the attestation manager key. Of course, the private key doesn't go anywhere, the signing key, but I have to make sure things that are appraising results do have access to the public key. Okay, so now what we do, now we're where we wanted to be. At this point, we've executed our story, so to speak, and we're where we want to be. And where we want to be is we boot to an initial measured state. We effectively make sure, as I pointed out, we make sure we're running a good operating system that was booted properly. We then set up our attestation manager, and now we start to do periodic measurement. So we talk about runtime measurement. We're talking about running and observing long-lived systems that will run over extended times. So we want to do repeated measurement to make sure that our system stays in a good state. And so what this diagram is supposed to represent is the system coming up on the left, and then as time goes by, we can remeasure by rerunning our attestation protocol, we can remeasure our top-level device, our top-level system. We don't remeasure the operating system. We don't try to do that, other than we do remeasure LKIM. We do remeasure Linux with LKIM as a part of our protocol. So this was the, yes?
Sorry to interrupt. So are you assuming, maybe this is a naive question, but are you assuming that the binaries you're measuring are all statically linked? Or is it possible that they're loading shared object libraries and maybe at runtime, and maybe some of them aren't even really linked and they're getting dynamically loaded? And I'm thinking in terms of something like Postgres.
Sure, absolutely. So that's actually a really nice question. For LKIM doesn't, our hash checkers do. LKIM doesn't assume that things are statically linked, but the hashing the programs that we use right now do. And we know we need to write some more sophisticated measurements in that, and I'll come to that as we close. But the things that are hashed, of course, have to be statically linked. Initially, when we built this thing, initially the things we were measuring were written in a language called KML that does, in fact, statically link everything. And the cross-domain system that we're doing is actually written in OCaml with static linking turned on. So yes, and I apologize, I should have mentioned that, but to do more than that, we have more work to do. So now we talk about layering, we talk about runtime. Now we want to, I'm sorry, I should mention really quickly the tool suite that we use to build this out. So given a protocol, and I'm not going to go into this, it's discussed in several of our published papers, but given a protocol, we can synthesize the infrastructure that we need to appraise it. This is pretty important for our sponsor. Our sponsor is not going to get in, or actually no one is going to get in and write all of the infrastructure needed to execute a protocol. As I said, I'm not going to go into this other than to say that we do synthesize configurations for attestation managers, and all of the synthesizers have been formally verified. So adversary goals, thinking about what the adversary goal is, the primary goal is the adversary convincing us to trust something we don't want to trust or we shouldn't trust. A secondary goal would be convincing us not to trust something that we should. We've not really addressed that issue at all in our current work. But why we need to think about this is now the thing we want to do is test the running system. The thing that we hadn't done, and we don't know of, certainly of the runtime attestation that we do, we don't know of many examples of long-running tests. So we wanted to empirically analyze what we'd done, and we have to think, therefore, about what kinds of attacks an adversary might execute. So we start thinking about what kinds of things the adversary might do to the target, everything from replacing binaries, attacking our system infrastructure, attacking LKIM, attacking Linux. There are a whole host of things that might go on, and we tried to enumerate those as best we could. And then what we did is we used a tool called Chase that was developed by MITRE. What Chase does is it develops, in effect, it looks at your protocol, your Copland protocol, and it enumerates possible attacks. It enumerates the possible ways that that protocol might be defeated. So we went in and took our protocol and we ran the Chase analyzer on it. These pictures, I won't try to explain these, but these pictures document various different attacks. And we take those attacks and turn them into tests. So what we're doing is we're trying to generate tests that are that provide some degree of coverage over the protocol that we've run. The testing results, wow, this is hard. It's really hard to get people excited about an attack that didn't work. You know what I mean? It's so we were able to run various different kinds of attacks. We targeted components, we targeted configurations, we targeted executables, we ran attacks over the lifecycle, and we were able to detect the attacks we should have been able to detect. That's not a very exciting thing, except that we did detect the attacks we were supposed to. We believe at this point that the biggest thing we have left to do is more extensive testing. I am not satisfied with the testing. Well, I'm happy with the results we got, of course, but we need to do more. We need to do a lot more long-term testing. We need to look at tactile issues. There's some other things that we need to do as well. So, kind of wrapping up here and talking about what we learned, several things. One of the things that we have struggled with over the years is kind of separating boot time and runtime. So that key that I talked so much about is kind of our link from our boot system or our operating system to our user space systems. And coming up with a way to make that jump was actually hard. We thought a long time about how can we have the indication of good boot reflected in the evidence that we gathered about a system in user space. And we need to do that. Coming up with that key was a trick. It took a long time for us to come up with that mechanism. The AM signing key is critical. We spent a lot of time on it. We went through all kinds of machinations to make sure that that key was protected and that only the right attestation manager could use it. And that was worthwhile. That was very much worthwhile. Interestingly, though, we thought it would take a month to do. It ended up taking about 6 months to figure out how to get that key protected. Design for attestation. One of the things that is really interesting is I said that the cross-domain system was written by someone else. It wasn't written by the people building the attestation system. And that's true, but that someone else knew about attestation, and he knew about the techniques that we were going to use. And what he did was wrote a system that was easier for us to appraise. It didn't do it on purpose. That wasn't what he was thinking about, but it kind of naturally came that way because of the way that he thinks about systems. So what we started to do, and it's not in this presentation, but what we started to do is define mechanisms that people can use in their designs that make them easier to appraise. And I'll give you a great example. The filter component and the rewriting component in our cross-domain system are the natural way I would have written those is as processes. So a process would sit and watch a port, pull messages in, do its thing, spit messages out. Okay, so if we do that, the way we appraise it is we have to do introspection of its runtime state. And that's not the easiest thing to do, but we can do that. We know how to do that. But the way Joshua wrote the cross-domain system was instead of having these things be processes, they started, processed messages, executed their filters and rewrites, and then went down, then terminated. What that means is we don't have to measure that long-term running state. But it does mean that the initialization files become absolutely critical, absolutely essential. But they're trivial to measure. Hashing a file is not a hard thing to do. So it's absolutely trivial to produce those measurements. So this idea of design for attestation is a real thing that we're going to be thinking about a lot as we move forward. The other thing we learned is, and this was something that we kind of knew that it would be far easier to verify and formally model the attestation system, the measurement system, than it would be to any target. And that turned out to be very true. The attestation manager, verifying the attestation manager was a PhD thesis. It was a few hundred lines of code. There were some things that made it a little bit complicated to verify, but it's been done. And we've done it once and we don't need to do it again. And it is simpler than any of the things that we would monitor with that attestation manager. So we leveraged a lot of formal verification by focusing on this smaller subset of things that we could get our hands around pretty easily. So that's kind of what we learned here. It was a good experience. It took way longer than we thought, but we were able to bring our system up. We were able to take the techniques that we developed over the years and apply those in this domain. So we were pretty happy with where we ended up. However, I want to make this really clear. This is a story. I'm not proposing this as the way forward for runtime attestation. I'm proposing it as an example of how we might do it and where we might start. And I think that's really important. There's a lot of work left to do in there, but we didn't want to dive into that work until we were confident we had a story. So what's up next? Long-running attestation. I've talked about that some. I think looking at a system over weeks and months and years is a very interesting thing to do. We want to look at larger layered targets, and when I say that, I mean we would like to be able to scale this up to systems or to domains. We'd like to be able to look at this building, for example, would be a wonderful one. Can we appraise the devices in this building and assemble that and scale this up to very large systems? Evidence is program understanding. Really interesting things going on. I've participated in a couple of workshops with DARPA about program understanding, and this will be a shock to you, but we've written really large systems that we don't understand. I can't believe it. So one of the things we hope we can do is characterize kind of runtime envelopes for running systems and be able to appraise whether they're operating inside or outside of those normal envelopes and make some contribution to this notion of program understanding. One of the last things I wanted to mention in this audience is separation issues amongst our AMs and the attestation manager and ASPs. One of the things we have not verified, we have not shown, is that you can't do bad things with ASPs. You can't go in and use ASPs together to actually launch an attack. We did, however, restrict all of our ASPs to only being able to read. They cannot change the state of the running program in any way. That gives us some level of protection, but we really need to do some separation analysis on our ASPs. And the attestation manager it's single-threaded. As I said, it's verified, but we would still like to do some different analysis on that besides just that it executes it executes protocols properly. Lastly, people are friends. As I said, this was a lot of my students at KU, Josh Gutman and Paul Rowe at MITRE, and then Jim Carter and Steve Smalley and Daniel DeGraff at NSA. Steve was the one that suggested I come here, and I thank him for that. This has been a fun couple of days. So, are there any questions? Yeah.
So, thinking back to some of the work discussed by Anna in her talk about TDIS, have you thought about adding layers later on? And a sort of follow-up question, if you have, is what does detaching look like after that? Which I also asked that.
So, yes, we've thought about those things, and then we stopped. And the reason is I felt like that we needed to build this first. We needed to get this in place first. We have lots of really interesting plans for detaching is actually one thing that we've thought of. We also have issues of migration that we have to deal with. The idea of building, so we have this layer, this attestation manager layer. Can we build other attestation manager layers on top of that, multiple attestation managers that work? We've written a couple of papers on that, but haven't implemented anything there. So yeah, we have thought about that, but I don't know. I would do it again. I would still say again, we're not going forward until we can at least do runtime measurement of a simple system that we didn't write. Yes.
You mentioned that this is for long-running systems. Long-running systems have bugs and need to get patched. How do you handle attestation of the kernel and the operating system in the face of live patching or kexec or anything like that?
We haven't done that. Just I'll be very honest. I'm not gonna lie. We haven't thought about that. But that is one thing that keeps getting brought up by one of our sponsors is Department of Energy site that worries very much about that, and they're pushing us that direction. But one of the problems attestation in general has is maintaining the attestation infrastructure over, as you said, system changes. So what happens when your hash values change, which happens all the time? If you're doing any kind of upgrades whatsoever, we haven't tried to manage that. We've thought maybe we could use some PKI infrastructure to do that, but that hasn't been a very satisfying solution. But we haven't had a chance to deal with that yet.
One other quick one. You mentioned that the AM key is a long-lived key. Is there a reason the AM key isn't ephemeral? Because you are reevaluating everything. Couldn't the AM key just be an ephemeral TPM backed key?
That's a really good question. It's not something we thought about. But it could be if you, I understand what you're saying. We just haven't thought about that yet. That's interesting though. I'm going to take that up. Yes.
You go first. Sure.
Yeah, regarding the patching cycle process, right? So you want to slide into that, and ideally you're applying the same process to the patch. So when you get something, you know it's a valid patch, because what you're trying to do is detect I have a hash change. That's a valid hash change,
yes.
Right? So in theory, if I publish a patch for a known system, all those config, binary, and other things, I should be able to tell you what your outcome hash is. Like
Yes.
you apply the patch and it should match this, and then get deviations from that. So I guess it'd be a factor of integrating this process over into the patch, and then some kind of controller to detect when a valid patch shows up.
Yeah, so actually in a perfect world, the world that we would like to get to is that one would deliver all of the, let's call it the attestation material, along with an application or a patch. So one would, in the same way, I don't know, you can check an MD5 hash for the application you just downloaded. One could get the patch of the application with the attestation stuff and load it in. Now, one of the things that Pete Lascoco I worked with Pete a lot in the early days of this stuff, and one of the things he was very interested in was this notion of hot patching, of being able to maintain the system. And I have to be really honest, I didn't understand his kind of obsession with that, but he was right. And I hate to say that. I mean, I'm glad Pete's not here. But yes, for those of you who know Pete, you can say. But we in a perfect world, we'll be able to deal with these things, but we just haven't yet. We just haven't dealt with that yet.
So could you go back to the picture with the tests, the slide with the tests on it? Yeah, so this one. Have you considered, I mean, given that you're layered, looking at doing, bring only so many layers up and then doing the tests and seeing, and being able to prove what which layers protects against which attacks?
We didn't do that in this set of tests. We brought the system up. Actually, I take that back. We did a little bit because it's much easier to go after things like SELinux policy and whatnot early in the boot cycle. But we didn't really do that. But I think I understand what you're asking, identifying where something gets caught we haven't really tried that, but it's certainly something we could do. As I said before, I believe I said it, one of the things that I'm just not quite completely happy with is the level of testing, is the level of evaluation that we've done. We hope to get more, but as I said, there are things that I thought would take a month that took 6.
I've got more as well.
Oh, okay. We'll take turns then. On the point you made before about bringing the evidence along with hot patching things, my concern is that I'm not convinced it's theoretically possible, because fundamentally you're building a stack of things where future measurements are done by the next layer. And if you have to replace a bottom layer and you can't go back to the hardware and have the hardware remeasure without rebooting, and you have runtime state that you don't measure, and we're only talking about code measurements, I think the problem I'm concerned with is people assume attestation tells them things that I don't think it does.
Okay.
And people assume, because in a long-running system, the reason we're patching the system is there was a vuln, there was a security bug. And that's why we patched. So we can't tell you for sure that the vulnerability was not exploited before we applied a patch. We can tell you that the patch got applied fine, but we can't tell you you didn't get exploited. And because the exploit happens in those runtime, in those data structures in memory that we don't look at in any of this, we have no idea if you're running a secure system or not, except that the attestation tells you you are. And so it's sort of lying to you a little bit, is my concern. Yes.
I can't, how do I say this? So the easy thing to say is that if your system passes attestation, it's trusted. That's the easy thing to say. What I say when I'm talking with others is, if it passes attestation, I know that the policy that was defined at that time is not violated. And there's a big difference there, right? But it's a lot easier to sell trust than it is to sell adhere to policy, right? So you're absolutely correct. But you did bring up you did cause me to think about another project we're working on, which is maintaining measurements over time. And when we learn different ways of appraisal, being able to go back in time and figure out, figure out where, as you said, where something was exploited that we couldn't see when it occurred, but we could go back in time and look at it. I think that would be a useful thing to do. We just haven't. We've been looking at ways of using blockchain to capture that and in an involatile way. And there's some interesting things we can do there, but it's very, very early work.
So 2 points on that. Firstly, I think there are also a number of other reasons that people who aren't security people patch, and that's because there are changes in capability, whatever it may be, and we should think about those as well. The other is I can imagine a world where you have certain components which are installed and attested, which act as canaries, which might be able to say that certain other components, particularly if they're not in the direct installation or execution chain, it might be able to say, I think that bit has not been tampered because it's outside the set of things that were tested in my range, and therefore, if you're doing a sort of Merkle tree attestation where you're bringing stuff together like that, you might be able to cross-certify that something is still safe, and that might give you options to do things. Very unformed thought, but Do you see what I mean?
Sort of.
Sorry, that went pretty cool.
Yeah, I do sort of, but
Cool.
the part of it is so many of the attacks are going to modify state that is an effective policy.
Yeah, well, of course.
And so you have the effective policy that says the security in that kernel data structure should have said this for that process. And I went and modified that, and some other piece of code might not know that because it's not just the on-disk policy, it's all the runtime execution that got you there. So, hard problem.
And if we have time, I have. So if anyone else has questions, please, we should do this. But one final one, which is how hard have you thought about provisioning? Because provisioning is really hard for some of this stuff.
We've thought a lot about it, and it's hard. Hashes are just really awful things, I think. They're simple to calculate. I understand that that's all really great. But trying to maintain the body of hashes, and one of the things that we discovered early on, very early on, was the same stuff doesn't always give you the same hash, in the sense that we were dealing with Dell. It's not Dell's fault. It's not Dell's fault. But we were dealing with Dell home grade computers, right? The cheapest stuff you can get. And we were looking at a hash from a graphics card, different kind of thing. What we didn't realize was that it was the same computer, right? We had, I think, 6 instances of the same computer, but because they're consumer grade, whatever the cheapest graphic stuff that was available at the time got put into the machine, even though there's no indication of that. So we were very perplexed about why we were getting different hashes. And finally it came down to, oh, this is different hardware. That kind of stuff happens all the time. Provisioning hashes is painful. Doing what we call provisioning boot, where you bring things up to learn the hashes rather than check the hashes, that's not too bad to do until you start thinking about the number of different instances of machines you might have in any reasonable shop. And we've got to come up with solutions, and I hope we will, but we haven't.
I just feel like I've got to give an obligatory story time because I had some money from the Department of Energy a couple of years back, and I was looking at reactor stability. And I was doing a lot of sort of verification and modeling of control equations from sensor input values. And I had built not a direct hash-based system, but a robust system for extracting the control equation and checking the differentials from the power plant's read-in. And it didn't work. And I cross-checked my work for around 2 months, and I was like, why these equations that it's pulling out are exact? I've got a verification of this power plant. Like, what the heck is happening? And then I learned that the analog to digital converter that was translating the sensor reading to the digital value that was being processed by the programmable logic controller had scaling applied to it. So I feel the obligation to mention that to people in the Department of Energy, that systems are composed of many parts. So just, it's great work. It's one part of the equation. So.
Sure, absolutely. Is that it? Oh, I really appreciate the questions. Thank you, thank you.